All right, so this is part two of our electric potential and our electric potential energy um, recorded notes. And our part one ended here, so I'm going to start here with part two. So the electric potential decreases as you move away from the charged particle. Lines of equal potential are always perpendicular to the electric field lines and point toward the decreasing potential. So we know around a positive charge that the electric field lines go out of a positive. Okay, so as we go further and further away, we get to a lower potential as we go further out. So closer to it, we have a higher potential, and further away, we have a lower potential. And these are created as spheres or domes around the charge of potential. Okay, so the thing to realize is our electric field lines go straight out, and it makes a 90-degree angle right here with um, the electric potential. Okay, so down here again, as it comes out, it makes a 90-degree angle with the electric potential surface. Okay, so then if we talk about plates, okay, so it goes out of the positive and into the negative is our electric field. So the electric potential is actually um, cutting it across horizontally because our lines are going vertical here. Okay, so it's a set of parallel lines, and each of these parallels are just like these shells, but instead they're just lines and sets. So every point along this parallel is equal potential, and every one along this one is equal potential. And it's highest right here, and it's lowest down here, because this is the way the field would make the particle go. So we always go from highest to lowest. So it always, the electric potential decreases as you move away from the charged particle. So this is the charged plate moving this way with the field. All right. So no work is done if a charge moves on an equipotential surface, meaning if it stays on the surface in the same circular dome, no work is done. Work is required, though, to move a charge to a different equipotential surface. So if I'm moving it further out and the electric field lines go out, then it's going to decrease. And so that's going to be negative work because the field's going to do that. But if I move it inwards and move it to a higher potential, I'm actually going to have to do positive work. So all of these right here on the 70, okay, if I'm moving from the 70 to the 50, that's going to be done by the electric field. So that's negative work. If I move from the 50 to the 30, that's negative work. But if I move from the 30 all the way to the 70, that's going to take me doing work. So that's going to be a positive work. Okay, so that's kind of how you got to think about it. So if I change equipotential lines here, this is zero potential right in between them. So if I move from any of these lines outwards, okay, so from the zero into here, this is actually increasing the potential. So as it goes in, it's going to it's going to actually in well, hold on. As this one goes in, this is going to be where the natural way it goes. So the field's doing work. So the field is going to go this way as it changes. Okay. So the electric potential in a uniform electric field, all right, it's related in a simple way to roughly the electric field. So the change in the electric potential is known as the delta V. The electric field strength is just your E value, and the distance moved is our M. So if our electric field goes this way from left to right, then our D distance would be from this dashed line to this dashed line, and our delta V would be from this line to this line, because remember the electric potential is perpendicular to the electric field lines. So our dashed lines are our electric potential. So we would be going from the positive to the negative. So we could say that there's more potential right here and there's less potential here because that's what the electric field would naturally do. All right, so there's our equipotential lines drawn, and we can talk about that movement from one to the other. Now, U is our electric potential energy. It is not V, which is our electric potential, which is also known as voltage or potential difference. So remember, U is energy, and energy equals work, and work equals force times displacement. And force can also be written as E times D. And this E is electric field. So E times D would, or excuse me, E times Q actually is force. And then we would multiply it times D. Whereas our E times Q is our electric force. Okay, Q is our charge. So we could also say E times D is our electric potential. And V times Q is still our electric potential energy, which is U again, which could also be equal to M times G times H, which is all just a form of potential energy, which can then be equal to 1/2 mv squared, which this is the lowercase v, so it's velocity, and this is kinetic energy. So remember, energy is just a form of work, and work is just a form of force times displacement. And then force times displacement can be written in lots of different ways depending on what we're talking about. So remember that we can start to interchange all these formulas and set them equal to each other. That's going to be really, really, really important. So for spherical charges, vectors would be our forces, okay? If we remove a Q, then we now have our electric field. Electric field is also a vector, okay? If we remove an R value instead, we now get a scalar value, which is our electric potential energy. And if we remove an R value from this, we end up with our electric potential, which is also scalar. So these formulas are just different ways of either removing Q's or removing R's and talking about whether they're vectors or scalar. So oppositely charged parallel plates and uniform fields. We can say we've got electric potential, which is an electric field times displacement. Or we can say our electric field is our voltage divided by our displacement, or our electric potential divided by our displacement, or distance between them. It's not displacement really, it's distance between the plates. Now, on your formula chart, it's written like this, but instead of a D, it's an R. Okay. Then remember work equals F times D, which is under our mechanics section, but it also equals QE times D. Now, QE times D is not really on our formula chart, but E times Q equaling F is a rearranged equation, and um, yeah, that's really the only place it is. So that would be the way to substitute it on the formula chart. Then we know that work is also Q times V. So we do have that because it's written as energy. And we know that the work energy principle is the same. So the change in potential energy is the work. So work and energy is Q times V, which we have listed as changes on our formula chart. So we have our U equals QV, which we have a delta U on our formula chart and a delta V on our formula chart instead. And that's where I'm going to stop for now. If you think about it, we've covered all of the first 1, 2, 3, 4, 5, 6 formulas. We've sort of talked about the electric field formula. It's a little bit further down. And the only thing we haven't talked about at this point really is capacitors themselves. And that'll be our branch between our um, basic static electricity and our circuitry electricity will be our capacitors. They'll be our branch. So fun stuff. See you in class.